So for my winter 2021 Psych 195B Fieldwork and Cognitive Science course, I worked as a brain-computer interface intern at Everpedia. I started volunteering for the position a couple months prior to enrolling for the course with the objective of familiarizing myself with the project and also catching up with the kind of work that we would be doing at the internship. The project that Matthew and his team were working on at Everpedia involved developing machine learning models from steady-state visually evoked potential data, which is a form of EEG activity measurement commonly used for brain-computer interface applications in the visual field. Prior to working for Everpedia, I had some experience working with logistic regression models and some basic neural networks with limited layers. But my supervisor, Matthew, took a look at the logistic regression model I developed during this deep learning specialization course in order to find a starting point for my contribution so that we could work on from there. So the original logistic regression model was a binary classifier meant to accurately label images of cats versus non-cats. So it would only determine if a picture was a cat or if in that picture there wasn't a cat. It wouldn't say what else would be in the picture, it was just not a cat. So the original data set I used for this model was consisting of 209 images, all 64 by 64 pixels. And they were color images, so they had 3 RGB channels. And each channel represents red, green, and blue. So the overall dimensions of each image were 64 by 64 by 3. So 64 width pixels and 64 length pixels. It's a 2-dimensional image, and 3, which would represent each color channel, red, green, and blue. Once the model was trained, it was able to accurately label 70% of those test images that I would give to it of cats versus non-cats. So 70% of the time, be able to accurately label if something was a cat or not a cat. So given the rather low accuracy, Matthew suggested I try converting the images to grayscale, which would effectively remove the RGB dimension. So the input vector would simply be 64 by 64 by 1. Meaning that the picture would turn out gray, and it wasn't a matter of what color each individual pixel was, but just how bright it was from black to white. So I did change it to grayscale, and the model performed notably worse after doing so, with the test accuracy of 54%, which could possibly be attributed to chance at that point. It's so close to 50% that it makes the model almost useless. So just to make sure that nothing faulty was going on in my code, I wrote a program to open and show one of the gray images and make sure that it was actually a gray image. It turns out I would get a colored image every time when I would do this. So after some research, I discovered that the function I was using to show the image added its own default color key to it. And in this case, it defaulted to this color scale that was what's called viridis, which only shows colors between green and blue. This is an interesting detail because it wasn't affecting the model performance necessarily, because it's functionally the same thing as grayscale. Gray is from white to black only, and viridis, this color key that it was using, was green to blue. So it's basically the same thing as either bright or dark. Either way, the actual grayscale image that was being used by the model was actually gray, and it wasn't viridis. It was just this function that was showing it to me with this color, just so I could see it in that way. So reflecting on the difference between the RGB and grayscale models I designed, it just seems that the grayscale's quality of being simpler didn't necessarily make it easier for the model to extrapolate, but actually harder instead. The RGB model provided an extra dimension for it to find statistical patterns easier in the input. The model probably recognized colors and started, differentiating certain pixels easier and finding the patterns better. And this is an idea that doesn't generally apply to more advanced models that have high dimensionality. In fact, dimensionality reducing is a common strategy to improve model performance. And it's probably why Matthew suggested I take a look at the grayscale accuracy and compare it with the RGB. However, in this case, it was the opposite. The RGB was kind of necessary since the dimensions were really low to begin with. We concluded that logistic regression may not offer the performance gains necessary for our project and that we should explore other methods. My next step would be to work on developing a support vector machine model. SVMs are supervised learning models that analyze data for classification and regression analysis. However, since I had not yet used the project dataset by this point, I researched deeper into the data in order to understand what I was going to be working with first. The data was experimentally collected from SSVEP measurements on 35 subjects when they looked at specific visual stimuli on the screen. The stimuli itself was linguistic characters flickering at different rates each as to invoke a specific electrical response in the brain that could later be associated with a given character. So they would show subjects like a character, in this case, I believe it was Taiwanese or Mandarin, and they would just show them one at a time, each flickering at its own rate. So anytime, let's say the letter B in Mandarin, whatever the equivalent is, um, would show up on the screen and would flicker at the same rate every time you would see that character. So it's like, because they all flicker at different rates, it's like every unique character has its own kind of electrical response in the brain. You know, flickering light will induce a certain electrical activity in the brain, and for each character flickering at different rates, each one of them had a unique response in the brain. So the resulting input matrix X, that the extraction code that one of our partners had made, gave us an input X with a shape of 408 by 64 by 1500. So 3 dimensions. I was never sure what the 408 represented. I knew 64 was the amount of electrode channels that were on the subject's head monitoring their brain activity, while 1500 was the amount of time points across an experimental trial that would last for the whole length of a single character. So if they saw B on the screen, since time is continuous, we had to break it down into 1500 time points that we could see how between those time points how electrical activity would change. So in general, these dimensions just mean it's just representing the electrical activity going on in the brain of an individual while looking at any given character for every individual in the experiment. Basically, our entire data compiled into one single input matrix. The problem arises with the fact that our input matrix is 408 by 64 by 1500, is that it's a 3-dimensional shape, while support vector machines can only take a 2-dimensional input. So in order to reduce the dimensionality, I did a common technique of simply flattening 2 of the inputs together into one, and that way getting a 2-dimensional input matrix. So the way I did this was just multiplying 64 by 1500, and I got 9600, and I just kept the 408. So my resulting input feature vector was 408 by 96,000. I said 9600 earlier, that was wrong. So in some cases, flattening the input doesn't harm the interpretability of the data too much for the model, and it could still lead to a model that generalizes pretty well, even though at the sacrifice of removing a dimension. So after researching the meaning of all this data and reshaping it into something that I could actually use, I designed a SVM model with the scikit-learn Python library. And given that this is a classification problem, I used the support vector classification class offered by the SVM implementation in scikit-learn. And at the first attempt with default parameters, the SVM was able to achieve accuracy of 73%, which isn't too bad. And that was with default parameters. So I had that benchmark, and I decided that I would try and give logistic regression another chance with this new data set that I now have. So similar to SVM, logistic regression only takes 2-dimensional inputs. So that reshape that I did earlier was perfectly fine for logistic regression. And I just had to pass it in the same way. With default parameters, the logistic regression model was able to outperform the SVM on the test set with 77% accuracy. So just a 4% accuracy increase with a different model. But the good news is that I had 2 benchmarks that I could work with. I could start improving and parameter tuning after that. So, logistic regression, I tried as many parameters as I could. Any parameter of interest that could boost accuracy, I explored. There wasn't much though. I mean, the first thing I did was try to see which train test split would give me better accuracy. I converged on the 24% test split. So 24% of all my input and labels I used for the test set that I could later test after training the model. It gave me a slight boost. It gave me a 2% accuracy increase. And then I decided to change the solver to one called liblinear, which is the most adequate solver for using small data sets such as mine, and it gave me a 3% increase. So by the end of it, I had only gone from 77% accuracy to 80% accuracy. So I couldn't really improve it more than that. I tried every other parameter. I went to SVM, see how much I could push that one. And plenty of parameters showed some improvement. And I ended up landing on a 95% accuracy. So I went from 77%, I'm sorry, 73%, which was originally lower than logistic regression, all the way up to 95%, almost near perfect accuracy. In summary, the performance made a dramatic increase. With the SVM, logistic regression got a little stuck in the mud. And yeah, I think that was a pretty good advance, and it was good to experiment with the different parameters. In hindsight, I think I would have gone for a grid search method that would have helped me find the parameters easier and possibly finding even more accuracy. And I've yet to do that, but I will continue to do that. In general, I learned a lot about machine learning practices in this internship. It was really fulfilling to engineer these models and see how the performance would shoot up and when it would go down and why it would go down or why it would go up, and just look up, the reasons for this and start understanding, what's going on beneath the hood. And it was very fulfilling. The work I performed in this internship is just basically the exact kind of work that I would want to keep doing. I'm interested in applying machine learning practices to real world problems and discovering patterns in data that can help people make more informed decisions. And the specific brain-computer interface application has many possibilities for helping people with even, like, for example, certain motor disabilities. If we show a disabled person who can't move their body, certain things on a screen, that could activate certain patterns in their brain activity that could indicate what they would want to do. So if they look on something that, for example, flickers at a certain rate, much like in the experiment, it could mean that they want to turn left on their wheelchair, on their motorized wheelchair. Or if they look at something with a different rate that's also on the screen, they could tell them to go forward. So the BCI applications are pretty much limitless, and it's very exciting to do this kind of work. I only wish I had a little bit more time to explore all those different machine learning methods. And regardless, I appreciate the opportunity I received so much, and I look forward to keep on doing this kind of work in the future.